Section 4-5 is on the derivatives of the inverse trig functions. The objective of this section is to differentiate each of these 6 inverse trig functions, and then of course use those properties to find the derivatives of various functions involving inverse trig functions. So let's start off with here a little bit of a review of properties of inverse functions. And this is on page 148 in your book. I'm going to quickly go through this. I don't know that you need to make note of what we're covering here, but I just want to refresh your memory about the properties here of the inverse of a function. The first thing is that if y is equal to f of x, then the inverse of f is x equals f of y. In other words, the way that you find the inverse of a function is you swap x and y, and then generally speaking, we solve that for y if it's possible. The second thing here is another definition really for us. If the inverse of f is a function itself, then f is said to be invertible. So a function is invertible if its inverse is also a function. The third thing that they note there for you is just a little on notation. It says if f is invertible, then the inverse function is denoted by f, and we put a little -1 there as a superscript. That's not indicating raising it to a power. It just happens to be that's the notation we use. But we read that as f inverse of x. We only do that if, in fact, the inverse is a function. The next property that they give you there is if f is invertible, then the composition here of f inverse of f of x, turns out that's equal to x, and f of f inverse of x is also equal to x. So whatever function f does to x in that first case, f inverse undoes all that to give you back x. Or in the second case there, whatever f inverse did to x, plugging that into function f undoes all that and gives you x back. All right, and the last property here is just a little bit about the graphical representation here, the graphical features of this property. It says the graphs of f and its inverse are symmetric across the line y equals x. In other words, a quick way to sketch the graph of an inverse is to sketch the graph of f, sketch the line y equals x, and then just reflect function f across the line y equals x. It may end up being a function, it may not be a function when you get done sketching that reflection across there. But that, whatever you sketch there, that in fact is the inverse. All right, so those are the properties and definitions there of the inverse of a function. On the next page, they also show you the properties there for the inverse trig functions. And again, from pre-calculus last year, you saw these functions and you saw how to use them as well as the domain and range that they're defined on. And I just want to quickly go over them again with you here. And we'll use these actually in the examples in a minute. But it says for the first one, y equals sine inverse of x if and only if x equals sine of y. And the range of that inverse trig function is from -π/2 to +π/2. And the reason why we have a restricted range here is because of the fact that all of our trig functions are periodic, of course, which means that they repeat at regular intervals, which means that they are not invertible. The only way that we can make our trig functions invertible is by restricting the domain of those trig functions, which of course in turn means you're restricting the range of the inverse function. So that's what we have here, that we have a restricted domain on sine. It's the sine of y, and so this is the restriction on the input for sine, or that corresponds to the output of sine inverse, the y value there. So it's the domain on sine, but the range on sine inverse. And if you look at the quadrants there and measure angles in the 4 quadrants, if you're talking about an angle that's from -π/2 to +π/2, those angles will look will fall in quadrants 1 and quadrant 4. We'll look at the quadrants there at the very end of this just to refresh your memory on that as well. But that's the two quadrants that this inverse sine function is defined on. And we can do this for each one of these functions. So y equals cosine inverse if and only if x equals cosine of y. And this time, the range of your cosine inverse function is from 0 to pi. Now 0 to pi is quadrants 1 and 2. And the third one here is y equals tangent inverse of x, if and only if x is equal to the tangent of y. Again, you'll see that's the same verbiage we're using throughout each of these. However, the range is changing slightly for each one. For tangent inverse, the range is from negative pi over 2 to positive pi over 2, not including the endpoints there. That's because of the fact that tangent's undefined at those endpoints. You have vertical asymptotes there. And so that turns out to be, again, quadrants 1 and 4. Notice that's the same quadrants that sine inverse is defined on. And then finally, the last three of these, y equals cotangent inverse if and only if x equals cotangent of y. And the range for cotangent inverse here is from 0 to pi. That's, again, quadrants 1 and 2. Same two quadrants that cosine inverse was defined on. In fact, we're going to see that same thing continue throughout here. It's either quadrants 1 and 2 or quadrants 1 and 4 that the inverse function is defined on. Here's secant inverse. Y equals secant inverse of x if and only if x equals secant of y. And that, again, is defined on the range from 0 to pi, including the endpoints here, but not including pi over 2. And so that turns out to be quadrants 1 and 2. And then finally, the last one here for us, y equals cosecant inverse of x if and only if x equals cosecant of y. And that's defined on the range from, or the inverse trig function there is defined on the range from negative pi over 2 to positive pi over 2, but not at y equals 0. So that turns out to be quadrants 1 and 4. Whoops. Let me just change that there. Quadrants 1 and 4. Okay. Now, if you look at your quadrants there, you need a refresher as to why we know that these angles are in which quadrant. Here are the 4 quadrants that make up our coordinate plane. We have quadrant 1, 2, and 4 labeled. I left off quadrant 3 because, as you saw up above, none of these were defined. None of these inverse trig functions were defined in that range that involved quadrant 3. So if you're looking at an angle or a range from negative pi over 2 to positive pi over 2, here's negative pi over 2, here's positive pi over 2. So you're talking about angles that would fall in this range right here. And you can see that that would be quadrant 1 and quadrant 4, just like we've set up above. On the other hand, some of these we saw were defined from 0 to pi. So that's angles that fall in these two quadrants. That's quadrants 1 and 2. And so that's all we're doing there. Again, we're just labeling the angles there, starting in the positive x-axis there at 0, and counting counterclockwise there. You have pi over 2 as the positive y-axis. Pi would be the negative x-axis. And going backwards there from 0, you get a negative pi over 2 at the negative y-axis. So that's how we've defined what quadrants these fall in. And those will become important here when we go to look at these derivatives. We'll need to come back to this to determine where that inverse trig function is defined in order for us to find exactly what the derivative is equal to. One last thing for us to note is the following here. If you are trying to work with the 3 inverse trig functions that are not on your calculator, that's cotangent inverse, secant inverse, or cosecant inverse, this is how you evaluate those on your calculator. Cotangent inverse is defined as pi over 2 minus tangent inverse of x. And secant inverse of x is defined as the cosine inverse of 1 over x. And the cosecant inverse of x is defined as the sine inverse of 1 over x. Those are equivalent. So if you want to find those 3 inverse trig functions, that are not on your calculator, you have to rewrite it here in terms of the three trig functions that are. The first property, by the way, comes from your co-function properties. I don't know if you recall those from last year, but if you go back in the back of the book there, they remind you of those properties. You don't really need to remember that it's a co-function property, but that's what it is that brings this equivalency. And the other two are actually the reciprocal properties that lead us to this fact that secant inverse and cosecant inverse can be rewritten in terms of cosine inverse and sine inverse. All right, so let's get to the topic of this section here then, is to find the derivatives of your inverse trig functions. And we're going to start out with the derivative of the inverse tangent function. And actually, we're going to follow through with this first example. That's what the first example actually asks us to do. It asks us to find the derivative of tangent inverse. So we're going to start out with y equals tangent inverse of x. And I'm going to use the definition that we just went through there for inverse trig functions. And we said that if y equals tangent inverse of x, then that's the same as saying that x is equal to the tangent of y. Those two mean the exact same thing. It's just another way to write that statement there. In fact, I'm going to rewrite it actually this way. I'm going to write it the other way around. The tangent of y, doesn't really matter which way you write it, but just because we're going to want y to solve for y eventually here, or y prime, it's going to be easier to write it this way. The next step of this is to actually take the derivative of this equation. The significance of writing it in this form is it's in a form that I could actually find the derivative of this equation, because on the left side I have tangent. I know the rule for the derivative of tangent. On the right side I have just x. I know the rule for the derivative of that. So I actually want to find the derivative with respect to x of the tangent of y equals x, of that statement that we have. Now to do this, realize that it's no longer solved for y, it's solved for x actually. So we have what's called an implicit relationship here. So this is going to involve what's referred to as implicit differentiation. Now we've seen this earlier, back in chapter 3. They introduced you to this, and we're going to see this more at the end of this chapter. But I just want to refresh your memory on a couple of things to remember with implicit differentiation. That if you take the derivative of x with respect to x, that's d dx of x, you can move that x into the numerator actually and write this as dx over dx, which of course that's equal to 1. And then the other thing that we need to remember is that if I take the derivative of y with respect to x, that's where I get, if I move the y into the numerator, I get dy dx, or that's referred to as y prime. Okay, so as we go to take the derivative, just remember that these are the things that show up there as we go to take the derivative. My board has lost the calibration, so I'm going to have to fix that. I'll pause it real quick and do. All right, I think we're recalibrated here, so let's continue on here. So we want to find the derivative of the tangent of y equals x with respect to x. So as I do that, on the left side there, as I take the derivative of this, let's follow chain rule to do that. So think of tangent as the outside function, y as the inside function, and take the derivative. So derivative of tangent is secant squared. And chain rule says you substitute in the inside function, which is y. And then finally we multiply by the derivative of the inside, which again, derivative of y with respect to x, we just said that over on the right. That's called y prime. All right, and on the right side of this, we're taking the derivative of x with respect to x. And again, what we just talked about to refresh our memory over there on the right with implicit differentiation, that derivative, of course, is equal to 1. Now the question was to find what y prime is equal to. It said to differentiate y equals tangent inverse of x. So we want to solve for y prime. So let's just take and solve this for y prime. Divide by the secant squared of y, and I end up with 1 over the secant squared of y is equal to y prime. And that's nice. We could even rewrite this in terms of cosine if we wanted to, but the only thing I don't like about this is that I started out with an equation that was y as a function of x, and I end up with y prime as a function of y. And we don't really want to have a new variable introduced in this derivative. So I want to come up with what that is equal to. And the way to do that is to find out what the secant of y is equal to. And to find that out, we got to go back to those definitions of those inverse trig functions to do it. And I want to start out with actually the second statement that I have up here is the tangent of y is equal to x. So I have that the tangent of y is equal to x. That'll help me come up with a triangle with a relationship that fits this relationship, I should say. And so I got to go back and look at where tangent inverse is defined. Tangent inverse, if you go back to the definitions we just looked at for those inverse trig functions, it was defined in quadrants 1 and quadrant 4. So I'm going to start out in quadrant 1 and see what happens. In quadrant 1, if I sketch a triangle here in quadrant 1, I should be able to sketch a triangle, a right triangle, that satisfies the tangent of y is equal to x. So my angle here is y, and the tangent of y has to be equal to x. So I need a triangle that has a relationship that has the opposite side and adjacent sides giving me a ratio of x. I know that tangent is the opposite over the adjacent side. So I want the opposite side to be x and the adjacent side to be 1, because then for this triangle, it is in fact true that the tangent of y would give me x over 1, or that's just x. And by Pythagorean theorem, I can then find the hypotenuse. The hypotenuse, of course, is going to be the square root of 1 squared, or 1 plus the x squared. And so if I go back to what I was trying to find here, I was trying to find out what y prime is equal to. And we had that y prime was equal to, oops, it was 1 over secant squared of y. So I really need to find out what secant of y is equal to, and I can just substitute it in here. So secant of y, well, if I look at my triangle up here, the secant of y, secant's the reciprocal of cosine, so secant would be the square root of 1 plus x squared over 1. So it's the square root of 1 plus x squared over 1. That's what secant of y is equal to, but I wanted secant squared, so we have to square this thing. Notice what I've done here is I've got this back in terms of x. Let's go ahead and simplify that here. Of course, dividing by the 1 there in the denominator isn't going to affect anything, so I can just write this as 1 over. If I take that square root and square it, I end up with just 1 plus x squared. And again, dividing that all by 1 squared isn't going to change it all. So it turns out that if I'm in the first quadrant, and that would be values of x there, since that's the vertical component of that triangle, that's where x is greater than 0. This is x greater than 0. I get 1 over 1 plus x squared for the derivative. Let's take a look at what happens in the other quadrant. The other quadrant that we have to deal with is quadrant 4, we said. So in quadrant 4, let's sketch a triangle. Again, these are the two quadrants that tangent inverse is defined in. We'll sketch a triangle there, a right triangle. Again, my angle here is y, and I need, again, a relationship between the vertical and horizontal component of this triangle, or that is the opposite and adjacent side, that gives me x. So again, I'm going to choose x and 1. You can pick any combination you want here to get x. Pick the easiest two to work with. So x and 1 will do that. The hypotenuse, again, turns out to be the square root of 1 plus x squared. And so again, going back to what we are trying to find here, we're trying to find out what y prime is equal to. I know it's 1 over the secant squared of y. And secant of y now on this triangle, again, that's the reciprocal of cosine, so it's going to be the square root of 1 plus x squared over 1. Notice it's the same triangle, so we're going to end up with the same result here. It's the square root of, square root of 1 plus x squared over 1. And again, it's secant squared, so we have to square that quantity. And so this turns out to give us 1 over 1 plus x squared, the same thing that we got over here on the left. Okay. Here, though, because x is in the, or this is in the fourth quadrant, and x is that vertical component, here the x is less than 0. So in either case, whether x was greater than 0 in quadrant 1 or x is less than 0 in quadrant 2, we end up with y prime is equal to 1 over 1 plus x squared. Notice that when you start out with an inverse trig function, let me just scroll back up here. I started out with y equals tangent inverse of x, an inverse trig function. The derivative does not involve any trig function at all. Y prime is 1 over 1 plus x squared. That's it. Didn't matter what quadrant we were in, we got the same result. Now the reason why we had to look at both quadrants here is because for some trig functions it makes a difference what quadrant we're in. Just turns out for tangent inverse it didn't matter. All right, let's take a look at an example and use this property we just learned to find a derivative. Let's say that f of x is equal to the tangent inverse of 2x minus 1, and we want to find f prime of x. So we're just going to follow our rule that we just came up with here. F prime of x is going to be equal to the following. First of all, notice it's a composite function. Tangent inverse is the outside function, and the 2x minus 1 is the inside function. So follow chain rule. Chain rule says take the derivative of the outside function, derivative of tangent inverse. We just found out that was equal to 1 over 1 plus something squared. Again, think of that x that's in your rule as a placeholder for you. And then chain rule says you substitute in the inside function. The inside function is 2x minus 1. And then finally we multiply by the derivative of the inside function. Derivative of 2x minus 1 is just 2. So if you wanted to, you could put that 2 in the numerator, I guess, and write that as 2 over 1 plus 2x minus 1 squared. If you wanted to, you could square that binomial in the denominator and rewrite that as well, but I would leave it just like that. There's our derivative of tangent inverse of 2x minus 1. All right. Let's take a look at example 2, which is actually going to take a look at the derivative of the inverse secant function. This is example 2 on page 150. All right, and the process is going to look very similar to what we just went through for tangent, for inverse tangent. So we have y is equal to the secant inverse of x. And again, in that form, I don't have anything I can do because I don't know at all how to find the derivative of secant inverse. If I could write it in a form that I could find the derivative of, that would be very helpful. So we've already stated that saying y equals secant inverse of x is the same as saying the secant of y is equal to x. Those two mean the exact same thing, just based on the definitions we talked about on page 149 there. And in this form, I have the secant function, which I know its derivative. I have x, which I know its derivative. So again, it's in a form that I could find the derivative. But of course, this is what we call an implicit relationship, where it's not solved for y. So that means I got to use implicit differentiation to find this derivative. So let's go through this and find the derivative. Again, on the left side here, follow chain rule as you take the derivative of secant of y. Secant's the outside function, y is the inside function. So derivative of secant is secant of something times the tangent of something. It's the derivative of the outside. Chain rule then says you substitute in the inside function, which is y. And then finally, you multiply by the derivative of the inside function, which is y prime. Basically, anytime that you have a y in your equation, and you take the derivative, there better be a y prime that shows up as part of that derivative. And so that's what we're seeing there at the end. We're getting that y prime. And that's equal to the derivative of x on the other side, of course, is equal to 1. And the goal here, again, was to find out what's the derivative of secant inverse. So we're trying to find out what y prime is equal to. So solve for y prime. We have 1 over the secant of y tangent of y is what we end up with. And again, there's the derivative. The only thing I don't like is the fact that we have y in this derivative function. I'd rather have it as a function of x than y. I know actually part of this, if you go back up to the second step up here, I know the secant of y is equal to x, so I could actually substitute that in, but I still don't know what the tangent of y is equal to, so I still need to go through very similar steps to what we just did to find out what tangent of y equals. So, go back to the secant inverse function and look at the quadrants that it's defined in. Now, the easy part is the fact that all 6 of these inverse trig functions are defined in quadrant 1. So I know one quadrant to start with. Let me write down what we have here again. We're using the fact that the secant of y is equal to x, and we're going to use that to draw a triangle in 2 quadrants here. So again, we always know quadrant 1 is one of the 2 quadrants. So we'll start with it. So I'm going to draw a little triangle here in quadrant 1. And I'm going to mark this angle here as y. And I need the secant of y to be equal to x. So secant's the reciprocal of cosine. So I know that the secant of y is equal to the hypotenuse, which I'll call x, over the adjacent side, which I'll call 1. Again, any combination there will work that gives you x, but pick the easiest one. X divided by 1 gives me x. And then again, with Pythagorean theorem, I can find the third side of this, the other leg. And that's equal to the square root of x squared minus 1 squared, or just minus 1. And so again, let's go back to what we were trying to find. We were trying to find out what y prime is equal to. I know it's equal to 1 over the secant of y, tangent of y. But the question is, what is secant of y and tangent of y? Now again, you can look at the triangle to find out what secant of y is. We already stated up above here that we are using the secant of y is equal to x to construct this triangle. But if you check out your triangle, of course it has the property that secant of y is equal to x. Check out the tangent of y. Tangent of y would be the opposite over the adjacent side, which turns out to be just that square root of x squared minus 1. Divided by 1, of course, doesn't change it. So we'll just write x times the square root of x squared minus 1. So that's pretty nice. Let's see what happens in the other quadrant. Now, the other quadrant that secant inverse is defined in, again, if you go back to those properties on page 149, you'll see secant inverse is defined from 0 to pi. That's quadrants 1 and 2. So the other quadrant I have to consider is quadrant 2 here in this case. So for tangent inverse, because it was defined in quadrants 1 and 4, the range of it is in 1 and 4, those are the 2 quadrants I work with. For secant inverse, the range is quadrants 1 and 2, so those are the 2 quadrants I work with. So let's sketch an angle or a triangle here in quadrant 2. Now the angle y here is actually this angle, because it's got to be an angle that's in quadrant 2. It's got to be between pi over 2 and pi to get in quadrant 2. But the triangle we can construct with its reference angle would be this triangle. It's a right triangle. And again, I've got to have the secant of y is equal to x. So the secant of y, again, is the hypotenuse, which I'd like to call x, over the adjacent side, which I'd like to make 1. Again, that would be the easiest combination to use there, x over 1. The problem that I have in this case is that this triangle is in the second quadrant. So the horizontal component of this triangle, this horizontal leg, is actually equal to a negative value. So I can't use 1 on the horizontal leg. 1 is not a negative number. So I have to make it a negative 1, which of course if I make that negative, then I can't just use x over negative 1 to get x. I have to make that the opposite of x over the negative 1 to end up with x. You can see now that I have 2 different triangles here. This is why I'm going to end up with 2 different results in this particular case. And if you calculate the third leg of this triangle, or excuse me, the third side of the other leg, it would be the square root of a negative x squared, which is just x squared, minus a negative 1 squared, which is just minus 1. And so again, go back to what we're trying to find. We're trying to find out what y prime is equal to. It's 1 over the secant of y, tangent of y. We know that's what we're starting with. We just need to substitute with what in for those two quantities. So secant of y, again, that's the negative x over negative 1. That's equal to x. That's what we started with, that the secant of y had to give us x. The tangent of y, though, this time is going to give me that square root of x minus 1 divided by the negative 1, the opposite over the adjacent side. So now this is actually a negative square root of x squared minus 1. Instead of dividing by a negative 1, I'm going to, let me fix that. Instead of dividing by a negative 1, I'll just put the negative 1 out front there. So there's what we end up with. And I guess we can rewrite this then as the opposite of 1 over, actually let me put the negative in the denominator, 1 over the opposite of x times the square root of x squared minus 1. So you can see that the sign is different here. One's positive, the other one's negative. Now to look at what the value of x is here, the value of x here is your hypotenuse. The hypotenuse of this triangle is always positive. The distance from the origin to the point at the other vertex there is always positive. So in quadrant 1 over here, x is greater than 0. And in quadrant 2, again, the same thing is true. The hypotenuse has to be positive, so the opposite of x is greater than 0. So that tells me that if the opposite of x, let me just do that over on the side here. If the opposite of x is greater than 0, just multiplying by a negative 1 would tell me that x, and when I multiply by a negative 1, the inequality switches, would have to be less than 0. So in the quadrant 1, we have x is positive, and in quadrant 2, we have x is negative. So let's take a look at what that means here. My board is off again, so let me fix that real quick. All right, so we've got the board fixed here. So let's write down what we have then. We have that y prime then is equal to the following. I'm going to write it as a piecewise function here actually, because I've got two different domains to consider. Over here in quadrant 1, we found out that the derivative was equal to 1 over this x times the square root of x squared minus 1. And that was if x was greater than 0 in that quadrant. And we ended up with 1 over the opposite of x times the square root of x squared minus 1 if x is less than 0. So we have a piecewise definition for the derivative in essence. All right, but you'll notice here that in this case, if x is positive, then we end up with a positive value here for x, of course. And on the other hand, if x is negative, then that means the opposite of x would, of course, be positive. In both cases, in other words, you end up with a positive value out front. If I associate that negative sign with the x there, in both cases, because in the first case, x is greater than 0, so I have just x out front, that's a positive number. In the second case here, I have x is less than 0, so that means the opposite of x is going to be a positive number. If I had a way that I could easily represent a number that's always positive, that would be great. And over, that's right, we have absolute value. So I can write y prime is equal to 1 over the absolute value of x, because that quantity is always positive, times the square root of x squared minus 1. And that right there is our rule for the derivative of secant inverse. Again, notice that we get rid of the inverse trig function there. In fact, that happens for all of our derivatives. Anytime we take the derivative of an inverse trig function, the derivative does not involve a trig or inverse trig function at all. All right, so let's take a look at all 6 of our inverse trig functions. And here are all 6 of them. Now we're writing them out in this form here in 2 columns again, like we did with the trig functions and their derivatives, because there's a nice property from the column that we have on the left to the column that we have on the right. So the first one there, derivative of sine inverse of x, we didn't do that one, but it turns out that would be 1 over the square root of 1 minus x squared. You'd go through a very similar process to show that one. The second one is tangent inverse. We did that to start off with. Derivative of tangent inverse turns out to be 1 over 1 plus x squared. And the next one, secant inverse, turns out we just did that one, was 1 over the absolute value of the square root of x squared minus 1. Don't forget that absolute value. It is necessary to put that in there. Now, the nice thing about these, once I know these first three here that are on the left, they're cofunctions, that is the sine inverse and cosine inverse, tangent inverse and cotangent inverse, secant inverse and cosecant inverse. Their cofunctions are exactly the same, but the opposite result. So the derivative of cosine inverse turns out to be a negative 1 over that square root of 1 minus x squared. And the derivative of cotangent inverse is the negative 1 over 1 plus x squared. And the derivative of cosecant inverse of x turns out to be a negative 1 over the absolute value of x times the square root of x squared minus 1. So once I know half of these, I actually know the other half. In fact, I can follow that same property that we talked about with our derivatives of our trig functions. We can follow that same property here with our inverse functions. To find the derivatives of your co-functions, really the co-inverse functions there, in the right column, replace each of the inverse trig functions really there in the left column with its co-function and take the opposite of the result. That's the exact same method that we talked about to help you remember the derivatives of your 6 trig functions. So once I know 3 over here on the left, I can use that little tip there, that little note to help me remember the other 3 over there on the right. Okay, all of your co-function derivatives are negative. All right, so let's take a look at a couple of examples here. Look at example 3. They ask you to differentiate the following. So y is equal to the cosine of cosine inverse of e to the 3x. So this is a composite function. In fact, if it helps you put parentheses in here to see that, then do so. But cosine inverse is the outside function, e to the 3x is the inside function. So follow chain rule here. So we'll start out with the derivative of cosine inverse. Now we just looked at that one. Remember, it's the opposite of sine inverse of x when we look at its derivative. So it turns out it's negative 1 over the square root of 1 minus something squared. Again, think of that x that shows up in that rule as a placeholder. I like using those parentheses so I don't accidentally put an x there. Put the parentheses to help you out. And then chain rule says you substitute in the inside function, that's e to the 3x. And then finally we multiply by the derivative of the inside function. Now the inside function, e to the 3x, is a composite function, so follow chain rule again. Take the derivative of the outside function, that's e to some power. And chain rule says you substitute in the inside function, the 3x. And then finally multiply by the derivative of the inside. Derivative of 3x is 3. So here's our derivative then. It's a negative, I'll put the 3 in the exponential function in the numerator here, 3e to the 3x divided by the square root of 1 minus. If you want to actually square this out, you could. You'd multiply your exponents there, so e to the 6x is what you'd end up with. It's fine to leave it as e to the 3x squared, but you could also square that thing and get this as well. So there's the derivative of cosine inverse of e to the 3x. Let's take a look at one last example here. This one is involving cosecant. Secant inverse and cosecant inverse, those are a little bit trickier derivatives to remember. Remember, they involve 2 x's when we look at their rules. The thing that will help you perhaps with that is if you remember the derivatives of secant and cosecant, they also involve 2 x's. Derivative of secant was secant of x times tangent of x. And cosecant, derivative of cosecant x was negative cosecant x times cotangent of x. There was 2 x's that showed up in the derivatives of secant and cosecant, and there are 2 x's that show up in the derivatives of secant inverse and cosecant inverse. That might help you remember those as well. Anyways, to find the derivative of this, we're going to follow chain rule here again. So derivative of cosecant inverse, all of our cofunction inverses are negative. Actually, all of our cofunctions, whether they're inverse functions or not, the derivatives are negative. So it's going to be a negative 1 divided by, it's the absolute value of something, times the square root of something squared minus 1. That's just using the rule there for the derivative of cosecant inverse. And then chain rule says you substitute in the inside function, so it's an x squared plus 1 that goes here, and an x squared plus 1 that goes there. Again, use those parentheses to help you get this written correctly there with that inside function in the right spot. And then finally, chain rule says you multiply by the derivative of the inside, which is 2x. So if you rewrite this, I guess you could put the negative in the numerator too if you wanted to, but I'm going to write it as a negative 2x over the absolute value of x squared plus 1 times the square root of x squared plus 1 squared minus 1. And I'm just going to leave it just like that in that form there. There are some things you can get rid of. For example, in the denominator, x squared plus 1, that's a quantity that's always positive. So I could actually get rid of the absolute value there technically. But I'm going to leave it just like this in this form here. All right? And that right there is the end of this section for us.